Sorting is a classic problem in computer science. Given a list of elements, put those elements in the right order. Let's try writing a sorting function that consumes a list of numbers and puts them into the right order. We'll start with a relatively incomplete data definition of a list of numbers. A list of numbers is empty, or cons pair, we need that starting parentheses, of a number and a list of numbers. And then we'll need to start writing our signature, purpose, header, and unit tests for this sort function. So, sort numbers is a function that consumes a list of numbers and produces a list of numbers. Obviously, not unchanged. In fact, it will consume a list of numbers and puts them in order, producing a new sorted list. And then we get our header. Sort numbers consumes a list of numbers and does something, ... somehow. We're going to write 3 test cases, although I probably should do more. For now, we're going to have a check expect that says when you call sort numbers on an empty list, it's very easy. An empty list is sorted just by returning an empty list. So that one's easy. But we'll also have one for a already sorted list. So if we call sort numbers on a list 1, 2, 3, that should return the list 1, 2, 3. And then we'll have one more that's actually interesting. We'll call sort numbers on the list 3, 5, 1, and that should produce the new list 1, 3, 5. Okay? Now, we know the template for list handling function. So we should be able to insert that just for free up in our function definition. A function that consumes a list of numbers is always going to have a cond body with 2 clauses. The first clause having a empty HUNT test for the list of numbers, doing something, and then the other test being, is it a consa? If it is a consa, we know that we'll do something with the first of the list, and something involving the smaller caller of the rest of the list, like this. Alright, so we have our template. Filling in the base case is pretty easy. We know that if we're sorting a list of numbers and the list is empty, we produce a new empty list. But filling in the recursive case is a lot harder. I'm going to write some notes below to demonstrate what this function does, and that might help us think about it a little bit more. So, if we have a list of numbers, and we call the first of the list of numbers, that extracts an element from the list. Alright, simple enough. If we pass it list 1, 2, 3, that produces 1. If we call this sort numbers on the rest of a list of numbers, that's this expression up here, then that produces the rest of the list, but sorted. You know, it handles all the other elements and produces a new list that is properly sorted. And it'd be great if that just magically worked, because then we'd be, be pretty convenient. And using recursion, we just assume that it does. We make the problem smaller, we assume that we can hand it off to the completed function, and it will magically spit it back out, having already done all the work. Alright, let's think of some more concrete examples of this. If I pass in the list 33, 55, and 11 to my function, then first alon would produce 33. That'd be the first element of the list. This is just notes to myself, just to help myself understand this better. If I call the rest of alon, that would produce the list 55, 11. But if I called sort numbers on the rest of alon, then that should produce the list 1155, because it would have sorted this. How it does it? Who knows? Who cares? The recursive magic would just do it for us. Well, let's talk about this now. We know that we're going to be producing a new list from an old list, and the only way to create lists is using cons. So we know that cons is going to be involved. But if we just tried to cons the first element onto the rest of the sorted numbers, well, that wouldn't work. Because right here, if we just cons 33 onto the sorted rest of the list, we'd end up with 33, 11, 55, and that's not right. Somehow, we're supposed to put this 33 into the middle between the 11 and the 55. So we need to insert it into the already sorted list in the proper place. What if, just for a second, we assume we had a function that did that? We go up here and we write, all right, we'll just, insert in order the first of the list into our already sorted rest of the list. Delete, and add it in. So here we're just assuming that we had this function. We're just magically using this function that we literally just wished that we had. Hasn't been defined, isn't built in, so we still need to write it ourselves. Once we do, the program's done. The function will just work as we need it, assuming we pass our check expecs. So we can just define it now. All right, so we go down here. We'll say that we have this insert in order function. Based on the above, it consumes a single number and a list of numbers, produces a new list of numbers, since this insert in order is going to be the return result of sort numbers, has to return a list of numbers. And this function consumes a number and a sorted list of numbers, and produces a new list of numbers with the given number placed properly in the new list, new sorted list. And then we'll write our header. So we know that this is called insert in order. We give it some end and some list of numbers. So just some number and a list of numbers. And it does something. Magic. Good unit tests are going to be critical in figuring this one out. Let's think of a few cases. Well, as usual, the check expect for the base case, the simple case of inserting a number into an empty list, is usually pretty easy. In this case, though, it's not producing an empty list. Remember, the goal is to insert n into the list of numbers. It was empty before, but now it's going to have at least one element. So we'll make a new list that's just the new element that we're giving it, in this case 5. We'll also make 3 more unit tests. We'll have one where we're adding into the beginning of the list, one we're adding to the end, and one we're adding to the middle. So first we'll add to the end. We have some list, 1, 2, 4, and we're adding 5 to it. So the new result should be 1, 2, 4, 5. Then we'll make another check expect, this one inserting to the beginning, and for this time we'll pass in 0, 1, 2, 4, same list as before, and if we insert 0 into here, it should go at the beginning. The list is already sorted when we are given it. We're just trying to find where the new number goes. I'm keeping things a little bit simple with my lists. I'm keeping all the numbers distinct, but things will work out just fine either way in this case. Alright, this was my last one. It's the 3. It goes in between the 2 and the 4, so it's somewhere in the middle. Alright, so we have some good check expecs that we can work against. Going back to our body, we now get to use the list handling template that we so very dearly love. This is the cond with 2 cases, as always. One is that we have an empty list, in which case we do something. The other is that we have a cons pair, and we have to do something involving the first of the list of numbers and the insert in order for the rest of the list of numbers. But we don't know what yet. We know our empty case is just to make a list out of the elements, so that case is, once again, pretty easy. If someone hands us an empty list and tells us to insert n into it, we just give them back the list n. Just a list of one value, and that value is n. Our recursive case, as usual, is a little bit harder. In this case, we have to ask a question. Is the given n greater than or equal to the first element of the list, which is, incidentally, the smallest element of the sorted list? If it is, we know it belongs here in the list, at the start of the list, so we just cons it on. If it was less than the current element, then we need to insert it later in the list. So we use cons to keep this element at the front and make the recursive call. Let's break this down. We know that we're asking a question, and it goes either this way or that. So we know we need if. We've got to figure out what the question is, and then what the response is, either yes or no. So the question was asking, is the n that we are given in the function greater or equal to the first element of the list? In other words, the current smallest element of the list. If it's greater than it, then we know that this is where it belongs. So we'll cons n onto the list at the very start. It goes at the very front. I believe I have this backwards now. We'll come back and test this once we've unit tested it. Then the next question, though, is if it wasn't, then we need to put it later in the list. So we'll push it further along, and for now, keep the list unmodified. We'll cons this first element back onto the list, and we'll insert, in order, n on the rest of the list. All right, so I might have my logic backwards. Let's find out when we run the unit tests. Nope. Let's delete some old code so that we're not bothered by anything up here. Shouldn't be bothered by anything else now. Yes, we've managed to put things backwards. So I believe we need to actually ask if it's the other order. Yes, okay, very good. Okay, so if n was less than the current element, then we know that it belongs before it. This was the previous smallest element of the list. We asked if n is less than it. If it is, we put n at the start of the list, and we'll stop recursing. There's no recursive call in this case. The rest of the list is already sorted. We don't have to do anything else to the rest of it. But if it wasn't, we need to keep the current element where it is and insert it later in the list. So we do a recursive call on the rest of the list. This function was not easy to arrive at, and you see I even made a mistake very easily with my logic. But it eventually passed the unit tests, so that's why they are very valuable. From reading the original description of the problem, you almost certainly didn't realize we needed this insert and order function. But it did become more obvious after we started writing the function and realized it would solve our problems if we just magically had it. You have to be on the lookout for functions that you wish existed, because sometimes that's the right solution to a very difficult problem.